The position of the particle is given by the function s of t equals t cubed minus 6t squared plus 9t, where t is measured in seconds and s in meters. The velocity at any time t is the derivative of the position. The derivative of the position is therefore 3t squared minus 12t plus 9, where we use the power rule for each of the term using derivative shortcuts. What is the velocity after 2 seconds? We simply evaluate the velocity when t is 2. The velocity function is now 3t squared minus 12t plus 9. So v of 2 is 3t squared minus 12 times 2 plus 9. This is 3 times 4 is 12, minus 12 times 2 is 24, plus 9. 12 minus 24 is negative 12. Negative 12 plus 9 is negative 3. We just simply use a calculator. The unit for the velocity is the unit of the position, which is meters, over the unit of time, which is second. And so v of 2 is negative 3, or after 2 seconds, the velocity is negative 3 meters per second. What is the velocity when t equals 4? We plug 4 into the velocity functions, which is the derivative of the position. Then evaluate this. We get 9, and the unit is still meter per second. That is, after 4 seconds, the velocity is positive 9 meters per second. When is the particle at rest? The particle is at rest when the velocity is 0. And so the velocity is 3t squared minus 12t plus 9. When is the time? So we're looking for t. We set this velocity equal to 0 at rest, and we solve for t. First, we can factor out the 3t squared minus 4t plus 3 equals 0. And then we can factor the inside. T squared minus 4t plus 3 is now 0, divided by both sides by 3. This can be factored to t minus 1 times t minus 3 equal to 0. And so t equals 1 and t equals 3. These are the two moments when the particle is at rest. Next, when is the particle moving forward? The particle is moving forward when the velocity is positive. To solve this, we draw the number line and label where the velocity is 0 at first, 1 and 3. And then we check the sign of this velocity function. So this is the sign of the velocity. To check the sign of any interval, we pick a number on that interval, any number. For example, between 0 and 1, we would pick 0.5. If we plug 0.5 into the velocity, we would get 0.5 minus 1, which is negative, 0.5 minus 3, which is negative, and so a negative times a negative is a positive. Between 1 to 3, we can pick any number, 2 for example, and plug it into the velocity function. 3 times 2 minus 1, 2 minus 1 is positive, and 2 minus 3 is negative. A positive times a negative times 3 is a negative. And so the velocity is negative interval 1 to 3. On the interval 3 to infinity, we pick any number, 1000 for example, and plug it into the velocity function. We get 1000 minus 1 times 1000 minus 3 times 3, and so it is positive. And again, these two numbers are the time when the velocity is 0. By looking at this diagram, we see that the velocity is positive on the interval 0 to 1 and then 3 to infinity. And so we say that the particle is moving forward from time 0 to 1, and then after 3 seconds. Draw a diagram to represent the motion of the particle. This is a schematic diagram of the motion from 0 to 1. The particle is moving forward because the velocity is positive. It then moves backward from 1 to 3 seconds, and then is move forward again after 3 seconds. Next, find the total distance traveled during the first 5 seconds. This is the total distance traveled, not the displacement and not the position. To find the total distance traveled, we would need to break this down to the interval where the velocity is positive or negative. We would have to find the distance on the interval 0 to 1. We would need to find the distance from 1 to 3, and then we would need to find the distance from 3 to 5, because the question asks us to find the distance during the first 5 seconds. The reason why we want to break this down to 3 intervals is because we want each interval to have the same sign. From 0 to 1, the distance traveled is s of 1 minus s of 0. S is the position function, so we just simply plug 1 into the given function and then 0 into the original function. We will get 4 meters. From 1 to 3, we would compute the displacement s of 3 minus s of 1. This means we take the original function s and we plug 3 into t and 1 into t and subtract the 2. The result is negative 4 meters. We should expect the negative 4 because the particle is moving backward. And so from 0 to 1, the distance traveled is 4 meters. From 1 to 3, the displacement is negative 4. Therefore, the distance traveled is 4 meters. And then lastly, from t equals 3 to t equals 5, we know that the particle is moving forward. We take s of 5 minus s of 3, plug 5 into the original function and at 3 as well, we get 20. And so the distance, the total distance traveled from 0 to 5 seconds is 4 plus the absolute value of negative 4 plus 20. So this is 28 meters. Next, find the acceleration at time t, any arbitrary t, and then find the acceleration after 4 seconds. The acceleration is the derivative of the velocity. The velocity is 3t squared minus 12t plus 9, and so the acceleration is 6t minus 12. After 4 seconds, the acceleration is 8 of 4 equals 6 times 4 minus 12. 6 times 4 is 24 minus 12, which is 12. The unit for the acceleration is meter per second, so meter per second squared. Graph the position, the velocity, and the acceleration between 0 to 5. If we factor the function s of t and solve for t, set it equal to 0, we will see that t equals 0 and t equals 3 as a double root. And so the graph would look like this from t equals 0 to t equals 5. We only need to go all the way to 5 because the question asks us to graph it in this window. Next, we graph the velocity. we saw that the velocity had two zeros, 1 and 3, and it is a quadratic concave up, and so we know that the graph of the velocity is a parabola up to 5 only. And then the acceleration is 12t minus 12, and so it is a linear function whose graph is a line. If we solve for t, we will see that t equals 2. This is the line going up. And so we have the graph of three functions: the position, the velocity, and the acceleration. This is the graph of the position. The red graph is the graph of the velocity, and the line is the graph of the acceleration. And then lastly, when is the particle speeding up and when is the particle slowing down? The particle is speeding up when the velocity and the acceleration have the same sign. We can do a sign chart. It would be easier that way. Or we can look at the graph. If we were to do the sign chart, then we already have the sign chart for the velocity earlier. 1, 2, 3. We know that the velocity is positive from 0 to 1, negative from 1 to 3, and positive from 3 to infinity. For the acceleration, we would construct another sign chart and find the 0. The acceleration is 0 when 2t minus 12 is 0, or when t equals 2. We check the sign chart and we see that the acceleration is negative for t on the left-hand side of 2 and positive for t on the right-hand side. From here, we partition the two number lines using any zeros from each of the line. We see that from 0 to 1, the velocity and the acceleration have the opposite sign, so we know that the particle is slowing down. The particle is slowing down when the velocity and the acceleration have the opposite signs, positive, negative, or negative, positive. And so to answer this question, we just simply look for the interval where the velocity and the acceleration share the same sign or have opposite sign. The particle is speeding up on the interval 1 to 2. From 1 to 2, both the velocities are negative and the accelerations are negative. From 3 to infinity, because on this interval, the particle has the velocity positive and the acceleration positive. The particle is slowing down from 0 to 1 because the velocity and the acceleration have the opposite sign. And then from 2 to 3. Usually, when we write the intervals and we combine them, we would use the union symbol. So 1, 2 interval union with 3, 8 interval. We could also get the answer from the graph. The graph of the velocity is the red graph, a parabola, and the graph of the acceleration is the line from 0 to 1. The graph of the velocity is above the x-axis from 0 to 1. The acceleration graph is below the x-axis. From 1 to 2, both velocity and accelerations are below the x-axis. From 2 to 3, the acceleration is above the x-axis and the velocity is below the x-axis. And from 3 to infinity, both graphs are above the x-axis. And so that is the same as the sign charts that we constructed.